Welcome back to the course entitled Symmetry, Stereochemistry and Applications. In the 11th week, we have started discussing about the various rearrangement reactions, and in previous couple of classes, couple of lectures, we have discussed about a few important rearrangement reactions. So, in the last class, we were discussing about rearrangement reaction involving an ether. So, we will discuss today now the rearrangement reaction involving a die-in system. So, this rearrangement is called Cope rearrangement. In this reaction, a diene compound gets converted to another diene compound by simple heating. So, this Cope rearrangement reaction is an example of sigmatropic rearrangement. Just like our earlier last class, we discussed about the Claisen rearrangement reaction. So, here in this reaction, if you have a compound which has two double bonds at a far distance like this, in a condition you have the double bonds in 1, 2, 3, 4, 5, 6. So, if it is suppose a 1, 5 die-in, this compound when heated alone at 225 degree centigrade or in a solvent, this bond gets rearranged and a few bond making and bond breaking process takes place simultaneously. So, the transition state that I am drawing here has a few dotted bonds, which means either those bonds are forming or those bonds are breaking. So, this is the cyclic transition state, where these bonds are forming and these bonds are breaking simultaneously. So, what should be the product? The product should be this one. A new diene after the corresponding rearrangement reaction. This reaction also happens through concerted mechanism, which means that the bond breaking and bond making processes take place together, and there is no chance of any cross reacted products. So, if we take a mixture of two compounds, namely these two, suppose, these two compounds and heat them together, from the first compound we will get this as a product, from compound A we get product A prime, from compound B we get product B prime. And there is no question of cross reaction between A and B to give you a new product C. So, this particular reaction proceeds through a cyclic transition state, as we have already seen, and the Ts in general adopts a chair conformation. So, if I draw the dyne slightly differently, this is the dyne molecule A drawn slightly differently. So, when the reaction takes place at elevated temperature, this rearrangement takes place. So, as a result, what we have is like a chair conformation of a cyclohexane. So, the bonds which are breaking and the bonds which are in the process of making are written as dotted lines. So, this is the cyclic transition state where two methyl groups are in the axial position and it is in the chair conformation. So, when the product forms, you get to see this product as this. So, this is the product and the conformation of the product is written here. So, this is how the Cope reaction can be understood through a concerted step mechanism. The next reaction that we would like to discuss is the Fry's rearrangement. When a phenolic ester is heated in an inert solvent in the presence of a suitable Lewis acid as a catalyst, and the product is hydrolyzed. A mixture of ortho and para acyl phenol is obtained. So, the reaction is like this. You have a phenolic ester we heat this in the presence of Lewis acid and number 2 we do hydrolysis. What we get is the corresponding rearranged product with the ortho substitution, ortho product and the corresponding para product as well. So, here the catalyst is anhydrous aluminum chloride and the solvent is either carbon disulfide or nitrobenzene. Because these are high boiling solvents and one can heat these solvents at a higher temperature. Fry's rearrangement occurs in the presence of UV light without a catalyst. That is called photo Fry's rearrangement. So, in case of photo Fry's rearrangement, if you have this compound, use the UV light in ethanol medium and what we get is a mixture of products. The ortho product, the para product, and a side product which is just the phenol. So, we should see what is the mechanism of this reaction using the Lewis acid as catalyst. So, in this case the reaction mechanism involves the Lewis acid aluminum chloride. So, in case of step 1, your starting material first reacts with aluminum chloride to form an adduct like this. And then that adduct dissociates into two components. Like this. So, in step 2, the adduct of the catalyst and the dissociated cation reacts, and a further intermediate is formed. Which then in step 3 elimination of HCl takes place in step 3. So, what happens is one of the chlorides from aluminum chloride takes up the proton and it forms the double bond here. Of course, when this bond broke, we should have a plus sign there, and that plus gets further neutralized to form this product. I should not write CH3, I should write it as R. So, that is step 3. Now, in step 4 is a step of hydrolysis. So, on adding water to this adduct of aluminum chloride with the phenolic OH, the product is released. And aluminum chloride is released as aluminum hydroxide, right. So, when you see that this particular cation, it can attack, it can connect to the ortho position, simultaneously it can connect to the para position. So, it is possible to have a second product along with this as the para substituted compound. So, this reaction does not go through a concerted step, so that only one compound could form. There is a possibility of formation of two different compounds in this reaction. Now, let us try to see one more new rearrangement reaction, which is called the Baeyer-Villiger oxidation reaction, which is also a rearrangement reaction. This Baeyer-Villiger oxidation involves an intramolecular anisotropic rearrangement. An anisotropic rearrangement in which an alkyl group with its bonded electrons migrates from a carbonyl carbon to an electron deficient oxygen atom. This is an oxidation reaction on aliphatic ketones to ester or their hydrolyzed products. With hydrogen peroxide or any organic peroxide compound. So, the reaction is very simple. RCO is my starting ketone. It reacts with a peroxy acid to give the RCOOR is the ester, and the peroxy acid gets converted to the simple anion, the acetate anion. So, this reaction takes place through a few steps, which I am going to show in the next slide. So, the mechanism involves a few steps. The initial step, where the peroxy acid is dissociated to peroxy anion plus H plus, and this H plus is then taken up by the corresponding ketone to form the adduct. Which is also resonance stabilized. So, then in step 1, this adduct reacts with the peroxy anion such that the anionic part attacks the electron deficient carbon and the C double bond O breaks to form this reaction intermediate. So, second step is the migration of alkyl group. So, once again, if this double bond forms back, this group moves from carbon to oxygen, and this OO bond, that is the peroxy bond, breaks. So, in step 2, the product is this one with the anion of the peroxy acid. So, I think somewhere we have missed the R prime, which we should continue, so that we know that this ester, this acid anion is from the peroxy acid, and immediately in this reaction medium it loses that H plus, and what you get is the corresponding ester with the release of H plus ion, right. So, we started with a ketone and formed an ester out of that ketone, which means this is a reaction where oxidation takes place and you get an oxidized product in this reaction. So, we will continue from here in the next lecture.